So the purpose of this video is to talk about the inverses of elementary matrices. And even though I'm starting off by stating a theorem, there's some really good practical information in here and some good shortcuts for calculating inverses of elementary matrices quickly. So the statement is that elementary matrices are always invertible, and their inverses, by the way, are also elementary matrices. And conceptually, this ought to make sense. So if you've got a row operation that, say, interchanges row I and row j, you should be able to undo this. And in fact, you just interchange row I and row j again in order to undo that particular row operation. If you think about multiplying a row by a scalar, this is also something that you can undo by going backwards. If you've multiplied a row by 5, then you would multiply by 1/5 to undo that. And likewise, if your row operation, say, adds 2 row 3 to R2, then to undo that, you would subtract 2 row 3 from row 2. So elementary matrices are invertible because you can go backwards with row operations. So let's see what these shortcuts for calculating those inverses are. So the good news is that all of these shortcuts are pretty easy. The first one we're going to look at are row exchanges. If you have a matrix that carries out a row exchange, it's its own inverse, which makes sense. Interchanging row I and j can be undone by interchanging them again. The inverse of a matrix that carries out scalar multiplication to a row is also easy to invert. That matrix would take the form of a bunch of 1s down the diagonal where one of them had been replaced by the scalar, c. So the inverse of this matrix is just going to be 1s down the diagonal, but then that entry will be 1 over c instead of c. And it's very easy to see that if you multiply these two matrices together, you're going to get the identity matrix back, which means that they are indeed inverses. It's a worthwhile exercise to convince yourself in the case of row exchanges that when you multiply these two matrices together, you get the identity matrix back. The last type of row operation is when we add a multiple of one row to another row. The elementary matrix that corresponds with that row operation looks like the identity matrix, but where one of the entries off the diagonal has been changed from 0 to a multiplier, like A. So the inverse of this particular matrix takes the form of 1s down the diagonal, but then negative that multiplier off of the diagonal. These shortcuts are all very convenient. There's going to be times in your coursework where you're expected to calculate the inverse of a matrix on its own or in the context of another problem. And these shortcuts for elementary matrices can really save you some time. So while we're on the topic of elementary matrices and their inverses, let me give you a handy fact. The theorem statement is that if you have a square matrix and you're wondering whether this matrix is invertible or not, that's true that it's invertible if and only if it can be written as a product of elementary matrices. And it's not so hard to prove this theorem, so let's go ahead and sketch out that argument right now. So when you have a theorem statement like this, an if and only if statement, there's two directions to prove. In the first direction, we're going to assume that A is invertible, meaning it has an inverse. So if it's invertible, that means that there's a series of row operations that you can apply to turn that matrix A into the identity matrix. We would write something like EA is equal to I, where by E I mean the product of matrices, elementary matrices that carry out all of those row operations that turn it into the identity matrix. Well, if EA is equal to I, then you can also write that A is equal to E inverse I. E itself is a product of elementary matrices, all of which are invertible, so E is invertible. So this means you can write that A is equal to E inverse I, and that's E inverse. So we write A as E inverse I, which is E inverse, noting that E and E inverse are products of elementary matrices. And this gives us the statement. It's a product of elementary matrices. The other direction is pretty straightforward. If you have a product of elementary matrices, each individual matrix is invertible, and so the product of those is going to be invertible as well. And that essentially is the sketch of this useful fact. Elementary matrices and their inverses are going to turn up in several different places. So I highly recommend practicing calculating them and keeping track of them when you do row operations.